The next thing we're going to do is learn how to take Laplace transforms of derivatives. And once we're able to do so, this will give us a new means of solving some differential equations. So let's start off by looking at the following. Suppose we want to find the Laplace transform of f prime of t. And let's suppose that f prime of t is continuous. So that we can do this, this is by definition the integral from 0 to infinity of e to the negative s of t f prime of t dt, which we know is an improper integral, is really the limit as b approaches infinity from 0 to b of e to the negative st f prime of t dt. We can approach this by using integration by parts. Let's let u be equal to e to the negative st, and we'll let dv be equal to f prime of t dt. We differentiate to get du. We integrate to get v. The integral of f prime of t dt, well, that's simply going to be f of t. So using integration by parts, we see that this is equal to the limit. As b approaches infinity, we have u times v, which is going to be e to the negative st f of t, evaluated from 0 to b, and now minus the integral from 0 to b of v du. That's negative s e to the negative st f of t dt. Couple things we're going to do here. So this is the limit as b approaches infinity of, I have the first term here, which is now evaluated from 0 to b. Notice this minus and this minus is going to make a plus. I have s, which is a constant with respect to t, so I can pull this s out, and we have the integral from 0 to b of e to the negative s of t f of t dt. Okay, so what's happening here? Let's evaluate this part here. This is going to be the limit as b approaches infinity of e to the negative s b f of b minus e to the negative s times 0 times f of 0. Plus, now if we look at this thing here, with this limit, if I go back to the improper interval notation, this is the integral from 0 to infinity of e to the negative s of t f of t dt. Okay. And that part, what this integral is, this is actually the Laplace transform of the function f of t, which typically we call f of s. Now, let's suppose, and we want to do this, suppose that the function f is of exponential order, as we defined in the last section. If f is of exponential order, then this term is equal to 0. Minus, this would be e to the 0, which is 1. So we get the negative of f of 0, and then what this thing is, this is simply plus s times the Laplace transform of f. So in total, what have we shown? We showed that the Laplace transform of the derivative f prime of t is equal to s times f of s, which is the Laplace transform of f, minus f of 0. We could do the same game. It's fair to ask, well, what would happen if we took the Laplace transform of a higher order derivative? What about the Laplace transform of f double prime of t? What would that give us? Well, the answer is you can find that out. using the same kind of work, you'd have to do 2 integration by parts steps. But what we would find out is that ultimately, if you work that out, the Laplace transform of the second derivative ends up being s squared times the Laplace transform of f, which we call f of s, minus s times f0, which is the original function evaluated at 0, minus f prime of 0. Similarly, if we did the Laplace transform of the third derivative, what we would find is we would have s cubed times the Laplace transform of f, little f, minus s squared times f of 0, minus s times f prime of 0, minus f double prime of 0. And this pattern that you're seeing, hopefully we kind of see it now, this pattern would continue indefinitely. The Laplace transform of the nth derivative, what it ends up being is the order of the derivative. So here in this case, n would be equal to 3. So what we get is s to that nth power, so it's going to be s cubed in this case, times the Laplace transform of our original function, little f of t, which we call f of s. And then we get a bunch of these lower order terms, which what you'll see is that the power of s will count down from the order of the derivative, 3, 2, 1, until you have no power, and then the function will kind of step up in terms of order of derivatives. The first one would be the original function f evaluated at 0, then you get its derivative evaluated at 0, and then you would ultimately end with its n minus first derivative evaluated at 0. So that information tells us how to take the Laplace transform of the derivative of a function. As we said a moment ago, it's going to be s raised to the order of your derivative, that's s to the n, and that first term gets multiplied by the Laplace transform of f of t, that's the thing we call f of s. From there, the powers of n will step down until you get to a constant term where there'll be no s at all. Meanwhile, you're evaluating the original function and its derivatives, which would be increasing in order of the derivative. So you have the original function at 0, the first derivative at 0, the next term would have the second derivative at 0, all the way until we get to the end, we have the n minus first derivative at 0. Okay. So, and also too, by the way, so we talked a lot about this. It's very important. How do we know that we can even take the Laplace transform? In other words, how do we know that this expression actually exists? Well, what we would need for that is to have that original function f and its n minus first derivatives to be continuous on 0 to infinity, and they would also have to be of exponential order. Okay. With the ability to do the Laplace transform of a derivative of a function, this is going to give us another method for solving linear ODEs. Okay, so it's very important here that the types we're about to look at, are going to be these constant coefficient ones that are linear. Okay. So let's suppose that we have our nth order linear differential equation, a sub n dny to nth derivative all the way down to a sub 0y equals to g of t. And let's suppose we actually kind of have those values we were talking about. If you have the initial value problem where you know the value of the function at 0, its derivative at 0, up to its n minus first derivative at 0, then what we can do is we can start off by taking the Laplace transform of both sides of our differential equation. Because the Laplace operator is linear, that allows us to take the Laplace transform of each term on the left-hand side individually. And of course, we can also factor out those linear coefficients. So it's going to be a sub n times the Laplace transform of the nth derivative of y with respect to t, plus pull out your a sub n minus 1, the Laplace transform of the n minus first derivative of y with respect to t, and then just keep going all the way down. And don't forget, you also have to do the Laplace transform of the right-hand side. Okay. From what we just saw a moment ago, we have a formula now where we're actually able to apply and take the Laplace transform of each of those derivatives. Okay. For example, for the nth derivative, it would be Sn y of s minus Sn minus 1, evaluate times y of 0, all the way down. The Laplace transform of y we know is y of s, and this is equal to g of s, which would be the Laplace transform of whatever your right-hand side is. Okay. Ultimately, again, let's keep our eye on the prize here. What are we trying to find? The ultimate goal is to solve for the function y. So we want to solve for what function y, let's think of it as f of t, makes this equation true. Well, once you apply the Laplace transform, what we end up getting is an expression that involves y of s. It's actually an algebraic equation at this point. Okay. We have an algebraic equation for y of s. The idea is if we can solve y of s and get it to be equal to a bunch of stuff, let me just call it, I don't know, h of s perhaps, then we can find our solution f of t. Remember, f of t is the inverse Laplace of, and I'm not sure why I'm writing it as y, I guess we could call it y of s, that's what the book does. Usually we call it capital F of s, but the inverse Laplace of y of s, which would be the inverse Laplace of that right-hand side, which is going to be h of s. So, to make a long story short, essentially what the Laplace operator does is it allows us to take our differential equation in the function y equals f of t and turn it into an algebraic equation in terms of its Laplace transform. We're going to solve that equation for y of s, and then ultimately the entire problem will boil down to being able to then do the inverse Laplace transform at the end, and if we're able to do that, that will give us our solution f of t to the differential equation. So in general, here's how we would solve an initial value problem by using the Laplace transform. Okay. So we would find an unknown y of t that satisfies the differential equation. We first start by applying the Laplace transform L. This transforms the differential equation into an algebraic equation in the function y of s. We can solve with algebra, solve for the function y of s, to get y of s by itself, and then when we apply the inverse Laplace transform now, what we end up with is the solution y of t to our original initial value problem. Let's take a look at one of these together. So let's actually use our Laplace transform to solve a differential equation. So let's take a look at example, what would this be, example 4? So in example 4, let's solve using Laplace transforms the following differential equation. dy dx plus 3y equals to 13 the sine of 2t, and suppose we're given the initial condition that y of 0 is equal to 6. This first time through, I'm probably going to write more than what I normally would write, but let's really kind of take our time to highlight everything that's happening here. The first thing we're going to do is we're going to apply the Laplace transform to both sides of the equal sign. So that's step 1. Because the Laplace transform is linear, this is equal to the Laplace transform of dy dx plus 3 times the Laplace transform of y, and this is going to be equal to 13 times the Laplace transform of the sine of 2t. From what we saw a moment ago, on the left-hand side, we know how to do the Laplace transform of the derivative. That's the thing that's currently new that we're working on right now. The Laplace transform of dy dx, that's going to be equal to s times, let's call it y of s. So it's s y of s minus y of 0 plus, and now over here we have 3 times the Laplace transform of y. We call that y of s. And this is going to be equal to 13 times, if you recall from our Laplace transform tables, the Laplace transform of the sine of 2t, that should be equal to 2 divided by s squared plus 4. We can simplify this quite a bit. So we have our s y of s term here. This is a plus 3 y of s. And now minus y of 0, recall that the initial condition we had was that y of 0 is equal to 6. So I can replace y of 0 with 6, and this is equal to 26 divided by s squared plus 4. We have an algebraic equation now. We now want to get the y of s by itself. So the first thing I would do is I would add 6 to both sides. We have s times y of s plus 3 y of s is equal to 26 over s squared plus 4 plus 6. We can now factor the y of s out of the left-hand side because it's a common term. That would give us an s plus 3 equals, and let's get a common denominator here to combine these terms. We want a single fraction, at least initially here. You would have an s squared plus 4. You could think of this as being over 1 times top and bottom by s squared plus 4. And that should give us a 6s squared plus 6 times 4 is 24. And then 24 plus 26 would give us 50. And now we have one more step left. To get the y of s by itself, we need to divide both sides by s plus 3. So y of s is going to be equal to, just simplifying this complex fraction, it's going to end up being s squared plus 4 times s plus 3 in the denominator. And so now we already know what the Laplace transform of our solution is equal to. All we would now need to do at this step is we would have to take the inverse Laplace transform of both sides, and that will give us a solution to our initial value problem. The only issue with that is, as we saw in the previous example, we're going to need to break this thing apart. We're going to need to use partial fraction decomposition in order to split this thing apart so we can actually apply our inverse Laplace transform rules. So starting off, we have 6s squared plus 50 divided by s squared plus 4 times s plus 3. And now it's going to decompose. And here's what's going to happen with our decomposition. So we have s plus 3, which is a linear factor, which means we're going to get a on top of the s plus 3. But then we also have this irreducible quadratic factor, s squared plus 4. And if you have an irreducible quadratic factor, when you're doing partial fractions, then you can have a linear function within the numerator. So the numerator could be of the form bs plus c. To solve for this partial fraction decomposition, we're going to do the same thing. I'm going to be lazy again. You should really show it on both sides as a multiplication. But essentially, we're going to multiply every single term in the equation by that denominator, s squared plus 4 times s plus 3, to clear it off. That'll give us 6s squared plus 50 equals when we distribute it into this fraction, the s plus 3's cancel, and that leaves us with an s squared plus 4. Plus, when we distribute it into the second fraction, we end up getting bs plus c times s plus 3. Now, at this stage, you can actually find one of the values by using the method we did in the last example. For example, if I substitute in s equals to negative 3, I would at least be able to find the value for a, because this term would cancel, and then, because that's the thing that makes this equal to 0 in the bottom, and then plug it into the left-hand side and work it out. On the right-hand side, though, there are no real factors that make s squared plus 4 equal to 0, okay? As over the complex numbers, we know that 2i and negative 2i would work. So I don't know if I feel comfortable saying that you can do that. It probably would work. You could make it work. But what I'm going to do, instead of doing a mismatch of methods, the optimal way, in my opinion, to solve this would be to use s equals to negative 3, plug it in, get the value for a. Once you know what a is, you have this concrete term. You would combine it with this concrete term on the left-hand side, and then that makes solving for b and c a little bit easier. But, as I mentioned in the last video, a lot of times if you have an irreducible quadratic factor, like we do with s squared plus 4, I also find that the method of equating coefficients works pretty nicely as well. So let's go ahead and do that. So what I'm going to do is expand this right-hand side. I'm going to distribute everything out. This is going to be as squared plus 4a plus first outer inner last this thing. You're going to have bs squared plus 3bs plus cs plus 3c. And now what we want to do is group our like terms and think of this as an equality of two polynomials in the variable s. So the left-hand side is like 6s squared plus 0s's plus 50. On the right-hand side, here's my two square terms. So we have a plus b, factor out the s squared. If I look for my y terms, excuse me, not my y terms, but my s terms, that would be these two here. You can factor out the common term of s, and we would have 3b plus c s, and then what's left over is my two constant terms. Combine those, think of them as just one constant. That's 4a plus 3c. And now what we can do is we can use the method of equating coefficients that simply says that the s squared coefficients have to be equal. Therefore 6 has to be equal to a plus b. So a plus b is equal to 6. Likewise, the coefficients of the s terms have to be equal. So 3b plus c So 3b plus c equals to 0. And then lastly, 4a plus 3c, that's going to have to be equal to this number 50. And now what we need to do is just kind of go ahead and solve for this. I'll do it. You can use the elimination method. What I would probably do, looking at it, is I might eliminate b by multiplying the first equation by negative 3. So if I multiply the first row by negative 3, that would give us negative 3a minus 3b. Actually, no, I don't want to do that. I don't want to. If you have a coefficient of 1, it's probably best to keep it as it is. What do we want to do? There's so many different choices here. Maybe I'll do that. That was the first thing I saw. I'll multiply the first one by negative 3. we would get negative 3a minus 3b equals to negative 18. And now I'm going to add that to the second row. When we add those two together, we get negative 3a, these cancel, plus c equals to negative 18. And now I can take that row with the bottom row from my original matrix, because that's two equations that involve a and c. And now what I'm going to do is multiply the top equation by negative 3. That'll give us a positive 9a minus 3c equals negative 3 times negative 18 should be a positive 54. We have 4a plus 3c equals to 50. And now we can add those together, and we get that 13a equals 104, and then simply divide both sides by 13. And turns out nice and neat enough, a actually ends up being equal to 8. And once you've found that first value, the rest of them fall then pretty easily. So once we know that a is equal to 8, we can plug that into the first equation. So 8 plus b equals to 6. Subtract 8 from both sides. We see that b is equal to negative 2. And then you can plug that into the middle equation to solve for c. So 3 times negative 2 plus c equals to 0. Negative 6 plus c equals to 0. So c equals to positive 6. So here's a good example of what it looks like if you use the method of equating coefficients. But this is good for us because now we're able to actually go ahead and split apart our y of s function. So the partial fraction decomposition for y of s, it looks like this. We said it was a over s plus 3. That's going to be 8 over s plus 3 plus bs plus c, where b is negative 2s and 6 is equal to c. And now that we did this, we can go ahead and find the solution by doing the inverse Laplace transform. So this is equal to y of s. Therefore, our ultimate solution, the solution to our differential equation y of t, it's going to be the inverse Laplace transform of 8 divided by s plus 3. And we can split this apart too, by the way. So let's split this apart. We have negative 2 s over s squared plus 4 plus 6 times 1 over s squared plus 4. We know that the inverse Laplace transform is also linear. So this is going to be 8 times the inverse Laplace transform of 1 over s plus 3 minus 2 times the inverse Laplace transform of s over s squared plus 4. And then we have a plus 6 times the inverse Laplace transform of 1 over s squared plus 4. We can now go ahead and do each one of these individually. For the first one, this is going to be 8. This is going to be e to the negative 3t for that part. We now are going to have a minus. This thing here is just simply the cosine of 2t. And now we've got to be a little bit careful with this last one. What we would need to have is we would need a 2 in the numerator. But then we'd also have to divide a 2 on the outside. So this ends up being plus 3. And then this is going to be the sine of 2t. And there's our solution. In my opinion, it's maybe just one of my personal favorites, but the way in which a Laplace transform can change a differential equation into an algebraic equation is huge. Because up until this point in your math career, you've spent an extensive amount of time working with and solving algebraic equations. And if you're able to Laplace transform a differential equation, then it really involves just two more steps. Being able to algebraically solve for y of s, and then applying the inverse Laplace transform that we focused on at the very beginning of this section. So very, very powerful method. Highly advise being able to do this as a general practitioner of somebody that solves differential equations.